Martin Korth, Universität Ulm, Germany.
Yeah, hi, I'm Martin. I would like to talk about molecular materials. And these materials are materials which consist of single molecules. Like, for instance, water consists of H2O. But there are, of course, many, many more other molecular materials, like organic liquids, for instance. And many of them are actually of very, very critical importance for devices like electrochemical energy storage devices, organic photovoltaics, or also molecular electronics. If we now want to do new materials to really improve these devices, we have a big problem, because currently, so to say, we have to have a good idea, and then we may have to make experiments, and we have to be a little bit lucky with these experiments. So in the end, it's very, so to say, highly educated trial and error. Why can't we simply check all these materials, like really look at all of them, and then, so to say, always pick the best one? The reason is very well known from virtual drug design. The problem is atomic Lego, so to say. Even if you have only very, very few, also there's no later point to show you, very few elements which you actually want to have in these materials, and even if the molecules are tiny, there's a practically infinite amount of structures which you can construct. This is, as I said, very well known for virtual drug design, and because all the knowledge we have about chemical spaces actually comes from that part. So if people from pharma companies here, they will, so to say, agree that this is really a very essential problem of developing new drugs, because they also consist of small organic molecules for which you want to have certain physical properties. Now, in my research, I'm developing a toolbox to evaluate, so to say, in a computer, the properties of battery electrolytes. So currently, this, what I will tell you, works only for electrolyte solvents for batteries. But I think it's a first step, and it's clearly transferable to other materials also. This toolbox allows you to evaluate millions of compounds, and then, so to say, go down to probably thousands or hundreds. That's, of course, not really breaking a wall. It's just kind of reducing it by a factor of probably 1,000 or 10 to the power of 4 or something. But the more important part is that we have now found an algorithm which actually allows us to reduce this practically infinite possibilities to something which we can tackle with these computational methods, which will then allow us in a second step to reduce it to a number of experiments which we really can do. And the idea is a little bit complicated, but the basic idea is the following. So if we have this full space of compounds, then our algorithm allows us to cluster many of these compounds into large clusters of which we only have to test one compound, and then we can move on to the next cluster. And if we find a cluster where we really have to check a lot of compounds, then you can again cluster it, can again only check one compound in each cluster, move on. And so in the end, we can really reduce this to only a few million calculations which we have to do, and then reduce it to only a few, probably thousands of experiments which we have to do. Okay, so yeah, I think this is really the first strategy developed ever for addressing, so to say, the complete space of molecular materials for one application case. Yes.